All right, start recording. All right, so this chapter is not going to be on exam 1. This chapter is exam 2. So chapters 0 through 6 are what we're going to focus on exam 1, which is a little ways next week. Remember, Monday is no school. Tuesday, follow Monday's schedule. So the next time we meet will be next Thursday. Right? It's on the syllabus that way. All right, so we're going to get started with, let's not mute that volume. Okay, so next time we meet will be next Thursday, but chapter 7 is not on exam 1. From chapter 7 on, it does get easier in some ways, but it gets harder in others. All of you have had some introductory programming course to get into this course, right? Okay, most of you are 160. All right. If it's been a while since you took 160 or you didn't do so hot in 160, there are a lot of things that I rely on you knowing how to do in programming. Looping, functions, how to deal with modularity, which is the idea of breaking down a large problem into smaller pieces. All right. So this chapter is not a chapter about programming in C. It's a chapter about how C interacts with bare metal hardware. All right. It's actually a pretty good breakdown in the book. These different sections, these 7 sections, 1, 2, 3, 4, 6 sections, all right, break down things pretty reasonably in terms of how C is going to interface with this hardware. So, quick refresher here. In assembly, we only have register names. We've got registers 0 through 31. Maybe we could call things X, Y, and Z, but we know that those are just aliases. In assembly, you only get one instruction per line. We saw how with macros, we can make that a little bit better. We can write one line that does a couple lines worth of stuff, but at the end of the day, it's still one line, one instruction. The benefit of assembly is you control exactly how many cycles everything takes. You can tweak it, you can set it however you like. You have full control. The downside is you got 32 registers, that's all you got. Technically you have access to memory, so you in theory have infinite registers, but the more stuff you have to store in memory, the longer things are going to take because accessing memory takes more time than accessing registers. Contrast that to C. C, register names defined. I feel like that's not what I meant to write there. But you can do many things on a line. You can have lines that are hundreds of characters long. You shouldn't, don't do that. It gets cumbersome. But you can do many things. Okay, a single line can encompass many instructions. Unlike assembly where you have full control over the timing, in C, you're kind of at the mercy of the compiler. The compiler is going to decide the best way to do something. And we can see that sometimes that's a good thing because it can create better assembly code than us in some cases. And it's bad in some cases because it might not take our intentions into account. I think the most important part of C is there's a bunch of functionality built into C. When you start in assembly, you got nothing. You got the 131 instructions, and you have to build up everything from scratch. Maybe you could start writing some libraries of macros, but that's it. In C, we have a lot of built-in functionality. In C, we also have a shortcut to dealing with multiple sizes of operands. In C proper, on a desktop machine, we typically think about things as chars, ints, longs, floats, doubles, unsigned or signed. Each of these has a particular size in bits. All right. Anybody notice anything interesting about int? In 160, you were taught that int was a particular size. How many bits is an int normally? That's okay, so small multiplication there will get you to the right answer. 32 bits. And yet this chart clearly says an int is 16 bits. Reason we say that is because we're on a completely different processor. We're on an 8-bit processor. In this case, the int is a 16-bit. The char is 8 bits. So there is a better way of dealing with this, a little bit more portable way. So right now we're working on an 8-bit processor. There's no reason that we couldn't be working on a 16-bit processor, a 32-bit processor. So rather than using these words, which change depending on what you're sending your code to, we're going to use a built-in C library called standard types, which is included by default. And we're going to use this notation. Okay, uint x underscore t. The underscore t says type. Int says it's a integer. It's not a floating point unit. And the u is optional. If you put the u, it's unsigned. If you don't put the u, it's a signed number. X can be any number, 8, 16, 32, 64. Okay. That's how many bits this is going to represent. So if we say uint 8, that's going to be an unsigned char on this architecture. If you say uint 8 in Visual Studio on one of these machines, desktop machines in lab, it will still be an 8-bit unsigned integer, regardless of what it has to say. There is a C library that tells you what an 8-bit unsigned integer is. When I say int 16, that gets a little bit different because a 16-bit unsigned integer is called an unsigned int here. In a 32-bit machine or a 64-bit machine, oftentimes a 16-bit word is called a short. But we don't have to worry about that because we're going to use this notation. However many bits you want, throw it in there. It has to be 8, 16, 32, 64. Okay, but throw it in there. If you're trying to do this on a desktop machine, you do have to include standard int. On Atmel Studio, it's included by default. All right. So that's the first thing. When you create variables, because you have them now in C, you have to choose their size. You should always choose the smallest size that will get the job done. All right. Now, to actually create a C project, there's a couple of images here just to help you through. I think this is actually still Atmel 6, but the process is just about the same. New project. And before, you used to have to click on assembler. You don't do that anymore. Now you click on C, C++, and you want to select a GCC. GCC is the name of the compiler. C executable. You do not want ASF. You do not want C++. You do not want a library. You want an executable project. It's going to run on your processor. Beyond that simple change, the next step should be familiar. You have to choose the 328p. Where things begin to diverge again is what you're given. This is the default code that you get when you start a C project. And it's a little different. First off, what did you always have to include in a C project when you were taking 160 or whatever course you were taking? Standard I/O, because that told you how to interface with the basic hardware, the keyboard and the monitor or the console. Well, we don't use standard I/O in that context. We use a file called io.h. It lives in a subdirectory called AVR. So specifically, we're talking about the AVR I/O. It's very similar to why you had to include the M328p def.inc file. It tells you what the names of all the registers are, makes it C-friendly. It also provides an endless while loop. And here's the weird thing. When you were running programs in 160, they would run to completion. And what would you see at the end of every program run? Press any key to continue. What would happen when you press that key? Somebody else. I know that you're awake. I get it. It would exit the program. That window would close. You go back to the operating system. Well, the microcontroller doesn't have an operating system. When you leave that program that you wrote in 160, let's say it was the STARS lab, because everybody loves the STARS lab. It's not going away. When you write that program and you exit it, there's still a program running on the computer. It's the operating system continues to run. From the moment the computer turns on, it is running a program, whether it's the boot system or the OS, it's running something. The only time that the CPU is not executing instructions is when it's off. Okay. Now your programs in 160 ended, they terminated and returned control back to the operating system. Your programs in this class never end. Okay. Think of your programs as Atreyu, okay? You guys wouldn't even get it. You have no clue who Atreyu is, do you? One person out of 40. Falcor. Makes me ill. The degeneracy of our youth. Anyway, our programs never end. So by default, they put a little while loop in here. It says while 1, forever. Keep doing something forever. And you have two choices. You can do what it says. You put your application code inside of this, and it'll run forever. Or you can leave it at the end of this and say just loop forever here at the bottom. So it runs through your code once and then stops there. It's still running, just like if you had said here, rjump here. It keeps running that instruction over and over again. And if you actually look, we're gonna compile this code and we're gonna look at what the assembly looks like to see what happens. So let's take a look now. We're just gonna hit compile on this program as it was given to us. And we need to talk about what happens. This is the output from the compiler. And when I say this is the output, it's actually page 1 of like 3 of the output. What it's saying here is it's gonna run a single executable, the compiler. The compiler takes C source code and eventually gets it down to assembly. But it does it in a couple of steps. First, we get it into an intermediate format. AVR GCC is the name of the program. The rest of this, purple stuff, these are all guidelines for how the compiler is going to do its job. Each thing says by default, anything that's 8 bits should be unsigned unless you tell it that it should be signed. Tells it where things should be packed as far as structures. Tells you warn all things. This is the big important one here. It says you're targeting the 328p. It says what version of the C language you should use. You should use the standard ratified in 1999. Do you guys know there were different versions of C? There are. There is a body that keeps coming up with additions to the standard. So this is 99. It's pretty reasonable and full function. The last piece of this says, this is where I want you to put my intermediate file in a .o file, an object file. And this is the name of the source file. So hello world.c was the name of my source file. It's going to end up in a compiled format in hello world.o. Then it has to build another file on top of that. So now it says, go back. It says, all right, we're calling AVR GCC again. This time we're going to build hello world.elf from the source file hello world.o. So now we're shifting formats a little bit. And again, we're targeting the 328p. So an ELF file is kind of like a zip file. Everybody know what a zip file is? It has a bunch of stuff in it. An ELF file not only has the .o file, but also all the debugging information you might ever need. Right? So ELF file is a container format. It keeps going. This was page 1. Page 2 continues on. Now what it's going to build is a file called the hex file. The hex file is what you actually send across the wire to the processor. It describes what every byte of ROM should be. So it's using a slightly different program now. Where's my mouse? There's my mouse. Use a slightly different program. It says, hey, build a hex file specifically from this ELF file that we just built. Call it hello world.hex. If you go back and look at your assembly programs, you'll see that a hex file was created for those as well. Hex is what the programmer uses to get data in. It also does one additional step. There's an additional type of non-volatile memory on the 328P called EEPROM. Does anybody remember what EEPROM was? What was it? Electrically erasable. So it needs a little bit of circuitry, which is inside of the 328P, and it can be erased and rewritten. So it's a little bit easier to rewrite than Flash, but it does exist. So we can actually store stuff in EEPROM. I know that I said in assembly you want to use .cseg for code, .dseg for data. Well, if you want to put something in EEPROM, you say .eseg, EEPROM segment. The last piece of this, which is the most important for our debugging, is it does create a listing file. So just like we created a listing file in assembly, with C we also get a listing file. I think I'm about to highlight like 8 things again. Yep, there they are. Those 3 files are created. Last page says, tell me how much of my ROM I've used. It says AVR size. This is a different program in the tool chain. How much have I used? And it says you've used 134 bytes. It actually says it in 2 places. Now, each instruction is 2 bytes, roughly, usually. So how many instructions do I have in this program? Hmm? 67. 134 divided by 2 is 67. Sounds about right. Right? 130 would be 65 plus 2, 67. Yeah. Wait a minute. Go back to the code. 4 pages ago. What does this do? Loops forever. And we said, can't we loop forever with that? That's 2 bytes. What the hell are we doing with the other 132 bytes? I'm glad you asked. At first glance, it seems like the C compiler shit at its job. For doing nothing, it needs 134 bytes? Send a man to the moon on that. Not really. Not by much. All right. What's going on here? Why are we using 134 bytes? Well, if you want to know that, you have to open up one of our debugging files, the listing file. Now, we saw the listing file before. We saw how to remove all the junk from the io.h file. And generally, it was just whatever our instructions were. Let's open up the listing file. It looks a little different. It's in color to start, which is actually pretty nice. I've got my address in purple. I've got the opcode in black. The mnemonic here is in blue. And then a little comment. And this is kind of nice now, because what it says is here, jump to 7C. Well, what the hell is it address 7C? The comment says, hey, 7C is this thing called bad interrupt. So it's a label. And in fact, at address 0, there's a label called vectors. You didn't write any of this stuff. The C compiler put it in there for you. All right, this is only the beginning. If we keep scrolling, we've got more. No, I've put a few notations. We talked about exclusive ORing R1 with itself. Right? That sets something to 0. 3F, it's not defined here what 3F is, but I tell you that 3F is the status register. So it's clearing out the status register. Right here, 8FF, that's the end of RAM. That's how many bytes there are in RAM. So what it's saying, when it puts that into 3E and 3D, That's stack pointer high, stack pointer low. So in some ways, this is a little bit more difficult to read because it doesn't have all of those things we've come to rely on. Names of registers. We don't have that anymore. But with a little bit of looking up in the data sheet, you can quickly come by this information. Finally, it says, call address 80, which again, yeah, you can go down here and look, there's a, or you could just say, that's the main function. This is a skill, being able to parse through this listing file. So you can see that there's a lot going on under the surface here of this very simple program that does literally nothing. It sits there and does nothing. So what do we have here? We've got bad interrupt. That's something I saw before. Bad interrupt, for some reason, we jump to it a zillion frickin' times. You won't get this for another week and a half, 2 weeks before we start talking about why bad interrupt exists. Okay? It's not just Rose Tyler telling us what's what. Bad interrupt. All bad interrupt says is jump to 0. So if you actually look at this code, it says, jump to 7C. So it jumps down to 7C. And then it says, jump to 0. Well, jump to 0 says jump to 68, which jumps back down to here. Now, let me ask a question that might put this shenanigans in context. What is the program counter when you first turn on power? It should be 0 every time. So if you jump to 0, that's basically the same as turning it off and on again. Okay? So jumping to 0 is kind of like resetting. So when you hit a bad interrupt, whatever that is, it tells you, put it on the board. It says causes reset. Thought I was being clever and asking questions. All right. Well, now that we've gotten through the first 7C worth of instructions, which seem to do almost nothing, now we actually, at address 80, finally get to our code. Our code says rjump dot -2. Period -2. Which is a little bit odd. We haven't seen that notation before. We always use labels. Dot stands for wherever the hell we are right now. -2 says wherever we are right now, -2. So since after executing this instruction, we're after CF, going back 2 bytes brings us to that again. So there's our jump here instruction. So all that extra stuff eventually leads its way to a loop that does nothing. It just stays looping here forever. But let's say we were bad programmers. Let's say in our C source code, we didn't loop forever. What would happen if we eventually got out? Because here we're calling. Get rid of all the ink on this slide for a second. We call main. So if we ever returned from main, what's the next line that would execute? Is that too small to read? It jumps to 82. 82 is a function called, or a label called exit. What is exit? What is CLI? That's an instruction we haven't seen before. Yeah, what is it? Say it again.
Global interrupt disable.
Global interrupt disable. It's actually saying the I flag in the status register is set to 0. Hey, didn't we hear something about interrupts a second ago? Wasn't there a bad interrupt? So, without knowing too much about what's going on here, definitely C is doing something with these interrupts. Which reminds me of my favorite joke. I get to tell it a week early. Let's see. Knock, knock. Interrupting cow. Moo! Laugh. Good job. Everybody gets 5 extra bonus points today. It's a great joke. It'll make more sense later, I promise. So CLI, and then what does it do? It falls through to this instruction. Hey, this looks familiar. R jump -2. So even if you are bad programmers and you don't heed my warning and you say, oh, I'll just return from main, C is smart enough to protect you from itself, or from yourself, rather. Okay? So, yes, we just spent 20 minutes talking about a program that does nothing. But all the pieces of it are important. This little snippet of code here sets R1 to 0, like I said it was going to. I told you for a couple of classes now, R1 is the register that C uses. It just assumes it's always got 0. Sets up the stack pointer so that we can automatically do functions, right? We have to set the stack pointer before we use a call. Otherwise, who knows where the stack pointer is pointing? And it clears the status register. So on boot, we assume that no status flags have been set. All right, let's talk about using C to do something for a second. Now, we've gone through a program that does nothing. Let's write some code that does something. We've already done time delays, right? Time delays are nothing more than loops that waste time. So here's a loop that does nothing. That's right. It's got just a semicolon here. That says for I equals 0, I less than 42,150, I plus plus, do nothing. Now, this seems to indicate that this will delay for 100 milliseconds. How did we come up with 42,150? Well, probably by experimentation. We probably delayed for 1,000 and measured how long that delay was, and then figured out, okay, if 1,000 is this many microseconds or milliseconds, this is what we need for 100 milliseconds. Now, this relies on something very important. Right? When we did our analysis of time, we found how many cycles, something took. A cycle is not a unit of time. Units of time are in seconds. How do we know how long a cycle takes? I really thought that was an answer. It sounded very much like a word, but it was just a straw. How long does a cycle take?
Frequency of the processor.
Well, the frequency of the processor definitely has some information that we can use. You guys should have seen this at some point, but capital T is the period of, say, a square wave. That amount of time. The period, tau, is equal to 1 over the frequency. Frequency is in hertz, cycles per second. And obviously you can rearrange this. The frequency is 1 over the period. So if I ask you how long something takes in seconds, you need to first figure out what the period is. Do I have a little calculator here? So if I know my system clock frequency, anybody know what the system clock frequency we're using on the processor is? Like 16 megahertz, yes. 16 megahertz, okay, is really 16 times 10 to the 6 hertz. So if I want to know the frequency, I can say 1 divided by 16, capital double E's, 6. And I come up with, where's my pen? 1 over the frequency is 1 over 16 meg. That's equal to 62.5 times 10 to the negative 9. What is the prefix for 10 to the negative 9? No, it's not micro. Nano. Nano. So that's 62.5 nanoseconds. Now, how many? If you've got a calculator, pull it out. I want you to do that operation. 1 divided by 16 times 10 to the 6. Because we need to address something right now. The question on the table is how many people get 6.25 e negative 8, and how many people get 62.5 e negative 9? I suppose a third option is 0.0000 something 625. Those should be the 3 possible options. How many people get option 1? Okay, how many people get option 2? How many people get option 3? Okay, option 3, get a new calculator. Option 1, you need to find a setting in your calculator that changes your exponential notation. There are 2 types of exponential notation. The most common is scientific. Scientific says, ooh, 1 number before the decimal place, everything else, and then the exponent. Engineering notation, which might be relevant to us in this major, throwing that out there, is going to make sure that your exponent is a multiple of 3, which is useful. Why? Prefixes. 62.5 nanoseconds. Instant. Done. Ready to go. 6.25 times 10 to the negative 8. Shit, all right, I got to move the decimal place over. Does that mean I add 1 or subtract? No, it's a negative number. What do I? Engineering notation. All right, on my little cheapy guy right here, this is a TI 30X2S, solar powered, never runs out of batteries. There's a little science engineering button. On a TI calculator, you want to go to mode, and one of the options is exponential notation. For a Casio, I have no idea. I can come and try to help you out. Sort of a side conversation there. Engineering notation is definitely where you want to be, because engineering notation actually helps you do math in your head. Because if you've got kilo something divided by micro something, you can tell what the resulting prefix is going to be. Kilo is 3, micro is negative 6. So at the end, you're going to have plus 9. Plus 9 is giga. So you can ignore all the times 10 to the whatever stuff, do whatever the simple division is, and then put mega as your prefix, or however you do it. Okay? So that is something there. Okay. What were we talking about before we started talking about that? Oh, that's right. Timing. It depends on your time. So we said that for 16 megahertz, our period, our clock period, so our frequency is 16 megahertz, our period is going to be 62.5 nanoseconds. So let's assume that we tune this using 62.5 nanoseconds as our period, a 16 megahertz clock. If my clock frequency changes and I run this same code, let's say I half my frequency. My frequency is now 8 megahertz. If I half my frequency, what does that do to my period? It doubles it. So now my period, 125 nanoseconds. What does that mean this delay is going to be? If I tune this for 16 megahertz and it delayed for 100 milliseconds, what does that mean about my new delay? Use the same function, all I've done is change the clock frequency. It's going to get less. It's going to get more. because our period is larger. So every cycle is going to take twice as long. So for the same number of cycles, it takes twice as long. So at the end of the day, if you find, and we had in our examples things like 5,050 cycles, then to figure out your time, you want to multiply that by 125 nanoseconds, or whatever, nanoseconds per cycle. Nanoseconds per cycle. So cycles cancels. You're left with a unit of nanoseconds. So that would be, what do we come up? 50 times 125 nanoseconds, e to the negative 9. Oh, I accidentally set myself into scientific mode. Okay. It would, no, engineering notation. Yes. So that tells me that this is going to take approximately 631.25 microseconds. If it was 50-50 cycle. It's not. That's not 50-50. That was from last time. All right. So if you're going to use this loop, there are a couple of things you need to keep in mind. First, the clock frequency has a direct effect on your delay duration. So this should really be titled delay 100 milliseconds at X frequency. The compiler actually can change this delay. Some compilers are so smart, they will try to save you time. They'll say, oh, this loop isn't actually doing anything. Let's just remove it. We want to be as fast as possible. So it'll remove it. So if you want to use this delay routine, you have to set your optimizations to not do that. Optimizations are set inside of the project properties. My project is named Hello World, so I go to Project, Hello World Properties. If your project was named Bob, it would be Bob Properties. It changes. So you click on those properties, and now there are a lot more properties. Remember, this is where you went to remove the include file in assembly. There's a whole lot going on here now. So you want to go to Tool Chain, Compiler, Optimizations, and make sure that your optimization level is set for optimized to size. That's if you're going to write your own code. All right? It's actually been taken care of for you. This is the big advantage of writing in C. In addition to making it easier because you're used to C, hopefully, there are built-in libraries. So there is a library called delay.h. And if you include that, now you can say, oh, delay milliseconds, delay for 1,000. Delay microseconds, delay for 1,000 microseconds. What you cannot do, you cannot say int x, actually I should say uint 8 underscore tx, right? 8-bit integer, x equals some magic function, and then underscore delay, that's what those red lines, those are underscores, delay underscore milliseconds x. Okay, you cannot put a variable into this function. It has to be a constant. This is the same type of thing that you could do in assembly, right? You could put in a .equ for an LDI, but you couldn't put in a register for an LDI. That would be invalid. So if you want to make some kind of a variable delay, you kind of have to wrap this around something. But delay.h, super helpful. Util. There are two places to find the delay.h file. And the way this kind of works is the folks who built the libraries put it in one folder to start, then decided they didn't like it there, moved it to the other place. So io.h is in a folder called AVR. There's also a folder called util. If you include it from either place, it will work, but you will get a warning. I don't remember if I fixed this or if this is the old place. I always have to check. Check it with util/delay. You'll get a warning that says, oh, this has been moved to AVR/delay, or you will get no warning and you know you've had it in the right place. So when you see that warning, don't be alarmed. It'll work, but you should keep up with what the library thinks you should be doing. All right. So delay milliseconds, super helpful. All right. Next thing I want to talk about, I/O programming. I/O in assembly was actually really nice. We had special instructions. We had SBI, CBI. We could skip if bit in I/O is set. We could do all this good stuff. Port names still exist in C. DDRB, port B, all that jazz. That is defined inside of IO.H. Tells you what it is. And you can use it as if it was a variable. It's not. It's technically a byte address that's been dereferenced. But you can pretend that it's a variable. So for your purposes, assume that every IO and extended IO register is a variable. You can read from it. You can write to it used by putting it on either side of the equal sign. So here's a pretty reasonable piece of code that is going to blink different parts of port B. It sets all of port B to be an output, turns them all on, waits, one might assume 100 milliseconds, and then turns half of them off, right? FF is 1, 2, 3, 4. 5 is 0, 1, 0, 1. So it turns off every other one. Delays 100 milliseconds, and it's a while one loop. Does it forever. There's a lot to be gleaned from this very simple program. It initializes a bunch of stuff at the top, and once it's initialized, it never talks to that register again. And then it loops forever doing something. In this case, it's making something happen, delaying, putting something else happening, delaying again. What that means is there's going to be an equal duty cycle of on versus off. And that's also something that's important. Okay, if they didn't have this second delay, you would be on for 100 milliseconds. Then you would be off, but you'd only be off for the time it takes to get back up to the top. So then you'd be on again. On, off, on. Okay. So when you're doing things like this and you want something to be symmetric, make sure to keep those delays peppered through appropriately. So that's a fairly straightforward one. You're setting all the bits at all times. Well, we could do that with an out instruction. Not really that much better. But C does not have a way for dealing with individual bits. Some compilers have cutesy ways. In the book, you'll often see them write things like port B.3 equals 1. All right, that's shit. As far as I'm concerned, shit. I don't know what this arrow is about to point to. Masking is what we call portable. All C compilers, regardless of provenance, know how to do masking. They know how to do bitwise and, bitwise or. Not all compilers know how to do this. In fact, our compiler specifically has no clue what this means. I think it's the IAR compiler. IAR is a company. They make compilers. They can do cutesy stuff like that. But if you want to move away from IAR, all your code is suddenly going to stop working. Which, from a business perspective, is actually kind of nice, right? Once you start using IAR products, you have to keep using them. It's like Apple. Once you start using Apple, you have to keep using Apple. It's a lot like Google. Once you put all of your personal information from Google, it's so easy. You get a new phone, it automatically downloads everything, and it's like you have the same damn phone. But if you want to go from Google to someplace else, not that there's any other place to go, worth going. I know that Apple is a company. I get it. Well, I guess we know where I stand on this issue. So masking is definitely the best way, and it's the best because it's the most portable. If you've got microcontroller code that runs on an AVR and you want to move to a completely different architecture, let's say you just want to move to an Intel architecture, by doing it with masking, you don't have to worry about if the Intel architecture has an SBI or a CBI instruction. Doesn't matter. Okay? C is the common denominator between those two things. The compiler will figure out the best way to do it. Brief reminder of masking, right? Logical operators are double ampersands and double bars, and the exclamation point. That is not what we're doing here. Logical takes the entire item and decides if it's true or false. 0 is false. Anything that is not 0 is true. And then it applies that. So you see here, this whole item is considered true. That whole item is considered true. So true and true is true. This is considered true. This is considered false. So true or false is true. This is considered true, so not true is false. That's not what we're doing. We're doing bitwise manipulation. Bitwise looks at every bit all on its own, and it uses single ampersands. It helps to think of this binary operation. It takes 2 operands. One of these operands is a mask. Here's my mask. Masks rely on 4 basic rules of Boolean algebra. X ANDed with 0, X ANDed with 1, X ORed with 0, X ORed with 1. So when you take X and you AND it with a 0, if it's a Boolean variable, it doesn't matter what X is. You're always going to get 0. If you AND it with 1, that's just like leaving it alone. ANDing something with 1 doesn't change it. ORing something with 0, likewise, doesn't change it. ORing something with a 1, though, doesn't matter whether X is a 0 or a 1. The result is going to be 1. So if I take this bottom thing as my mask, I'm ANDing with a bunch of zeros. Anything ANDed with 0 is a 0. So it doesn't matter what these upper bits are. The result is going to be 0 for those upper 7 bits. When I AND something with a 1, it leaves it alone. So this 1 is passed down to the option down there. Likewise, if I mask, same mask, but now the operation is in OR. ORing anything with a 1 means it doesn't matter what this is. It's definitely always going to be a 1. ORing something with a 0 means we're going to take all 7 of these upper bits and bring them down. So in masking, you can set a bunch of bits to 0 or set a bunch of bits to 1, either 1 or 0. By either ANDing with a bunch of zeros, that sets things to 0, ORing with a bunch of 1s, that sets things to 1. In fact, we did it yesterday or Tuesday when I showed 3 ways of setting bits to 0. One way was I loaded up a 0 in a particular place, 1s everywhere else, and then I did an AND. Okay. Finally, the inverse operator, the inverter operation, is a tilde. It's not an exclamation point. Exclamation is logical not. Tilde is bitwise not. So putting that all together, if I want to set bit 2 to be a 1, I can use something like this. 1 shifted left by 2 takes that 1, moves it over into bit 2 position. I say the second bit's position because I can start counting at bit 0. So it's bit 0 through bit 7. So shifted left by 2 sets bit 2. Shifted over by 0 sets bit 0. All right. So shifting operations are also used. So if you want to set a particular bit to 1. You need to make your mask have a 1 in that position, zeros everywhere else, and OR. If you want to build that mask, you use shifting. 1 shifted left by 4 builds your mask. And then it doesn't matter what all these x's are. Most of the x's are going to pass down because 0 ORed with x is x. 1 ORed with x is always 1. All right. Putting that all together in the C language, we can do some cutesy things. So this symbol right here is not a backwards flat face. It's not an emoticon. It is or equals. When you say port B or equals, that's the same as saying port B equals port B ORed with, logical ORed with, excuse me, bitwise ORed with 1 shifted left by 4, which is to say it sets bit 4 to a 1. So if you want to set a bit to 1, that is the portable best way to do it. If you want to set a bit to 0, you have to build that mask. Right? You have to put zeros where you want to set the result to 0. So to build that mask, it's a little more complicated. You can't just say 0 shifted left by 4. Because do you know what 0 shifted left by 4 is? It's still 0. You're not adding anything to this. So it's not enough to say 0 shifted left by 4. What you have to do, right, this is where you want that 0. So what you're going to do is you're going to build the opposite of that mask. 1 in that position, 0 everywhere else, and then do a bitwise negation. Okay? This is bit setting 101. So here's the portable way to do that. You say port B and equals, ampersand equals, and then you take the mask, you invert the mask, and you AND it. And that will clear that bit. Now this has some advantages in C, because let's say you wanted to set 2 bits to 0 or 2 bits to 1. Let's do setting 2 bits to 1 first. If I wanted to set 2 bits, maybe bit 4 and bit 6, I can do the following. Port B or equals 1 shifted left by 4 ORed with 1 shifted left by 6. So that is going to create a mask that has a 1 in position 4 and a 1 in position 6. OR them together. 2 masks OR together. 1s are common. So then when I OR that together, now I will have set a 1 in that position. Notice my parentheses. I say, okay, this whole thing together. That's what I'm ORing with. Setting 2 bits to a 0, it's the same thing. Port B, is there like a...
That's the alarm you set last class.
Yeah, like 3 classes ago, I think, actually, yeah. Is there like an ice cream truck outside? Or just people like have really big bladders or small bladders? What's going on? Well, finally, you learned from last semester. All right, port B. What was I saying? Setting 2 bits. What I would want is a 0 in this position, a 0 in that position. So here's what I'm going to do. AND equals tilde. And then in parentheses, I'm going to take those 2 masks again. 1 shifted left by 4, ORed with 1 shifted left by 6. So that together, just inside the parentheses, sets up the following. 0, 1, 0, 1. Yep. 0, 0, 0, 0. When I then apply the tilde operator to that, I get 1, 0, 1, 0, 1, 1, 1, 1. When I then AND that mask with my operand, I get a 0 in these two locations. So setting multiple bits either to 1 or 0 is just an extension of setting one bit. You just keep ORing things together. The thing you have to remember is that 1 shifted left by something is a number. 0 shifted left by something is always going to be 0. Okay? Apparently, example 718 does a lot of this. We did have a skip if bit is set instruction. So checking bits. It's as simple as taking your pin register, ANDing it with the bit you want to check. Now, if you take and AND a register with a mask, that clears out most of the items. So we're not talking about setting bits right now. We're talking about checking bits. So if you want to check just a single bit, the easiest way to check that bit is to determine, or is to remove all the other bits. Set them all to 0. So you take pin C, and this is pin C here, and you AND it with a mask of bit 5. That's it. It's all that's set to 1. Now, if bit 5 in pin C is a 0, what is the result? It's 0. If bit 5 is a 1, what is the result? 16 or 10 hex. Okay. Now, the if construct performs a logical operation, not a bitwise operation. So the AND here, that's a bitwise. But the if itself only looks at the logical truth. What is the logical truth of 0? Is it true or false? It is false. What is the logical truth of 10? True. So, that's the reason we leave it with no equals equals sign. That's enough to say if it's a 0 or a 1. If this whole statement is true, then we know that the bit is 1. It would be wrong of me. It would be very wrong of me to say if pin C and 1 shifted left by 5 is equal to 1. First off, it's wrong because you should have some parentheses here to make sure your order of operations happens. Let's put both versions up here. If pin C ANDed with 1 shifted left by 5 is equal to 0. And this is why so many people get confused. It is permissible to say that, because the options are either 0 or 10. But it's invalid to say this, because 1 is never going to be an option. It's either going to be 0 or 10, not 0 or 1. You're confusing bitwise truth with logical truth. So if you want to check if a single bit has been set, do not use equal. Do not use equal to 0. How would I check logically if this was equal? So this says if the bit is 1. How should I say if the bit is 0? If I can't say equals equals, use a logical operator. Logical not. Exclamation point. Pin C and 1 shifted left by 5. That says if it's not. So if it is a 0, then you will proceed. So why would you ever want to check if something was 0? Well, think about our button, our onboard button. That is set up in such a way that the button, which is a single pole, single throw button, one side is connected to ground. Internally, you should enable that pull-up resistor. This is inside the microcontroller, right? So when you press the button, it's 0. There you go. So that's why you would use a not. Very common to see that. Where people get into trouble is that because this is a valid way, technically it's okay. Right? Technically it's allowed. So they say, okay, yeah, great. Equal to 0, that's my button press. And then later on they copy and paste some code and they say, oh, all right, equal to 1. That's the mistake people make. They copy and paste and modify the code, and it makes a little sense that, okay, it's either 0 or 1. That's not the case. So the other way you could say it is you could say, all right, if it's equal to 0 or if it's not equal to 0. So if you feel that you have to use equal 0, don't say equal to 1 is the opposite. Say not equal to 0 is the opposite. Because if I changed my bit, if I changed that from a 5 to a 6, what would the mask be? It would either be 0 or 20 hex. So depending on your mask, different things are going to change. Now, this is not a conceit. This is not inflating my ego. There is a macro called _BV. Has nothing to do with me. It stands for bit value. If you say _BV5, it will automatically make the mask that has a 1 in position 5. All right? So it makes it very easy. You can just do that. If you wanted to do multiple bits, you would say something like tilde, open parenthesis, _BV5, or _BV3, or whatever your bits were. Okay? But the important thing is those parentheses for that tilde. You want to invert the whole thing after everything has been ORed together. Oh, we got 15 more minutes. We're fine. You guys are all packing up. I thought we were done. So, here's the problem, all right? As part of this class, you're expected to already have had C training. You should know how to program various types of things in C. At the very least, iterating over things, looping, writing functions, designing modular code. I don't have time in class to go over those things again. So if you are deficient in those areas, or you think you're deficient in those areas, you need to come see me outside of class, or you need to get remedial help at the tutoring center. Either of those is fine. For some of you, it's been a couple of semesters. For some of you, it's been a couple of years since you took 160. That's just how the out-of-step works. In terms of interfacing with the hardware, though, if you need help, there are a couple of places. First off, the manual for all of these libraries is at a place called no GNU AVR libc /user manual /mod, or you could, you could DuckDuckGo AVR GCC. Use whatever your preferred search engine is. You could Yahoo it. Yahoo! Yeah, Bing it. Absolutely Bing it. Anyway, just type in AVR GCC and it'll come up. You want that sort of 90s looking yellow background, static HTML pages. All right, it's where it's at. It's the manual. It has code examples. It has everything you ever wanted to know about every function in this library. It's worth poking around. Okay, so bookmark this thing. You're going to need it. You should definitely look up the files we talked about, delay.h, io.h. This is a file that's included by io.h, io m328p.h. Look at this file. Find it. Okay? If you include Atmel Studio, this file is on your computer. Look at it. All right? Okay. Let me just check where I'm at now. All right. Now, we're going to get into a bit, with the last 15 minutes, we're going to get into a bit of a touchy subject. Arduino. How many people know what an Arduino is? What's an Arduino? Go ahead.
Some type of processor.
No! It is not a type of processor. And this is why I get so angry about this. Literally, it's on the board and you still said it. No. Do you know what an Arduino is? It is a combination of a bunch of libraries and some hardware. Do you know what the hardware is? It's a 328P. It's the same thing we've been using. At the end of this class, you should, and I stress should, be so much better than all of these 12-year-olds who make LEDs blink and these art majors who go to Burning Man. You should be able to do hard things because you have full control of the hardware. Instead of relying on a shitty programming environment, a bootloader, oh, the bootloader, that's another big piece. All right. And these libraries that were written by people who have no background. Now, I'm not saying that all libraries are terrible. And in fact, the Arduino hardware is great. It's robust. It's very difficult to break. It's easily repairable if you have a little bit of soldering skills. There are a lot of things to like about Arduino. What I don't like about Arduino is what you just said. Oh, it's a processor. I'm going to use an Arduino processor. No, you're not. Okay? If you're going to use an Arduino Uno, you're using an ATmega 328P. If you're going to use an Arduino Mega, you're using an ATmega 2560. Same AVR core, same instruction set, different amount of memory. That's it. Different amount of pins. If you're going to use an Arduino Leonardo, you're using an AT32U4. Same instruction set, couple of different peripherals. What else do we got? If you're going to use an Arduino DUE, is that how you pronounce it? D-U-E? I don't care. If you're going to use an Arduino DUE, you're going to be using a 32-bit ARM processor. Completely different architecture, but same libraries, which is actually kind of a cool thing. That's one of the nice things. You can switch between different boards and your code will all work. Tons of development boards. There's an Intel version, there's an ARM version, there's a Wi-Fi version, all sorts of crap. It's not a microprocessor. And the biggest problem is it's not fast and it's not designed for multitasking. It does one thing at a time really good. Really well. Not an English major. Anyway, it consists of a programming environment. And I encourage you guys, it's on all the lab machines. I was the one who requested it get put on all the lab machines. I'm not an Arduino bigot. I just think that there are better things out there. This is it. It sets up, you can set up your code, set up your I/O registers, inputs, outputs, and then you've got a loop, right? I told you you could never return from your main program. Well, it forces you. It's just going to keep calling this function over and over again. You can target any board down here. It's an Arduino Uno on COM10, whatever that is. It's got a serial monitor, so you can just send printf statements all over the place. It's a development board. Here's the development board for the Arduino Uno. And you can't read it, but if you go and look at the high-res image on here, it says ATmega 328P. That's what it is. It's a 328P. You look at these cutesy labels, A0, A1, A2, A5. That's port C. It's just port C. Up there, 0 through 7 with little squiggly lines, that's port D. That's it. That's all it is. It's port D. 8 through 13, that's port B. There's nothing special about this, except there's a lot of things special. It's got a crystal. It's got a serial to USB converter. It's got lights on it. It's got a programming header. It's got voltages, 5 volts and 3.3. It's got a power supply. You just plug it into anything you feel like. You plug it into the computer. You can start talking and programming it immediately. It's awesome. It's got headers. It's a development board. It's a lot of development boards. It's a lot of them. And they all run on the same platform, the Arduino platform. It's a development board. We have a development board. Remember I said this was just port D. Well, shit, isn't that port D right there? It's port B. Well, that's port B right there. It's port C. Wait a minute, that's port C. It's voltage regulators. 5 volts, 3 point. Oh shit. 5 volts, 3.3. This is what we call Arduino compatible. Arduino compatible. You can actually turn this Atmel explained board into an Arduino compatible board by just putting headers in the right place. It's pretty nice when you get right down to it. It's pretty nice. All right. There are some differences in Arduino, and you should know about these. You should know how to use Arduino. I'm not going to talk about it after today, but go to any senior design team and ask them what the first thing they picked up was when they tried to start getting something up and running. Joe? What was the first thing you picked up when you started to try to work on your senior design project? What board did you pick up? You picked up an Uno. And then you decided that wasn't enough, so then you moved to a Mega. But your code stayed the same, right? You still just opened up Arduino and threw code on it. All you did was change a little setting that said Arduino Mega. All right, so it is useful for getting stuff up and running. Now, eventually, my advisee is going to move to just using a straight 328p in Atmel Studio, right? That's right. Like he would say anything else. So here's code on the right. This is how we're going to program all semester. Change which bits are inputs and outputs, while loops, checking pin D, port D. All right. With Arduino, it's a little bit different. In some ways, it's easier. I just say, okay, I want the pin mode of pin 2 to be an output. I want the mode of pin 4 to be an input with a pull-up. Okay. The code is the same across platforms, right? Pin mode 2 is pin 2 is an output. That's why I set pin 2 to be DDR. Pin 3 is an input. I don't have to do anything over there because it's just a 0. I don't have to add a 0 in. 4 is an input with a pull-up. That's why I write to port D. Makes it a pull-up. Here, I read from pin D. Here, I'm doing a digital read. I just want to know if it's a 0 or a 1. And I twiddle some bits high and low. In some ways, digital write is easier, right? I just say, oh, I want this one to be high. Well, at the end of the day, this freaking thing goes over here and executes that line. But it's great. What else is Arduino? It's a supply of libraries, okay? It comes with some built-in libraries. Then you can download. These are just recommended libraries. I don't even know what that means. And then there's contributed libraries. There's tons of libraries for every kind of component you ever wanted to freaking talk about. Chances are, if you can buy a breakout board for it, there's a library for it. That library will fail you. I promise. It will fail you in April of your senior design project because you will find that it doesn't work with another library. So, it's great for getting something up and running once. And then you need to take that information that you've learned and you need to put on your big engineering pants and your engineer hat and you need to code this up properly. So, tons of things. Too many to list. All right. And that's my rant. I feel like that's a better rant than I've done in the past. It's a pretty good one. Arduino has its place. Certainly, it's got uses. It is not a processor. And if I hear any of you in a couple of years in your senior design presentation going, we're going to use an Arduino processor, I will rip you a new one. Just ask this year's. Go find Eddie Pertel. Go find Patrick Ogyetti. Ask them what I did when they talked about an Arduino processor. Get out of here.